The name complex numbers sounds pretty intimidating, right? It makes you think, well, that they're complicated. But what if I told you that the math behind them is actually way simpler than you think, and that it unlocks this absolutely stunning visual secret? Today, we're going to break down the arithmetic of complex numbers.
But first, why do we even need special rules for these things? Well, let's start with a classic little paradox. Okay, we all know that 1 is the square root of 1. Simple enough. We can also write that as the square root of -1 times -1. Now, if you just split that root apart, you get the square root of -1 times the square root of -1, and we call that I. So you have I times I, which by definition is -1. So wait, does 1 equal -1? No. This doesn't break math, it just shows us that we need to have our rules straight.
And that's really the key thing to remember here. The rules for complex numbers, they aren't some bizarre new kind of math. Nope. For the most part, they are built on the exact same basic algebra skills you already have.
So what even is a complex number? It's just a number that has two parts. You've got the real part, a, that's just a normal number. And then you have an imaginary part, bi. And that little I is the star of the show. It's just defined as the number that, when you square it, you get -1. And here's the proof that you've totally done this before. Think back to algebra. You learned to combine like terms, right? You put the regular numbers together and you put the terms with a t together. Well, with complex numbers, it's the exact same thing. You just treat I like any other variable.
So yeah, the formal rules are pretty much exactly what you'd guess. Whether you're adding or subtracting, you just combine the real parts and then you combine the imaginary parts. It really is just about grouping like with like.
Let's just run it with some numbers. To add these two, 3 plus 2 is 5, and -4i plus 5i is just I. Boom, 5 plus I. For subtraction, 3 minus 2 is 1, and -4i minus 5i gives you -9i. See? Simple and clean.
Okay, addition and subtraction. Super straightforward. Multiplication is almost identical, but it's got one little twist. And this is the trick that gives complex numbers their real power.
We're going to start with an old friend from algebra class, the FOIL method. Yep, to multiply these things, you just multiply the firsts, the outers, the inners, and the lasts, just like you would with any other binomial.
But after you FOIL, there's one extra step. It's one new rule, and honestly, it's the most important rule in the entire game of complex number math.
This is it. This is the whole secret. Whenever you see I squared, you just replace it with the number -1. This is the key that lets you turn the imaginary back into something real.
All right, let's put this rule to work. First, we FOIL everything out just like normal. We get 4 terms, and you see that 14i squared at the end. Now for the magic step. We swap that I squared for a -1, so 14i squared becomes -14. After that, it's back to basics. Combine the real numbers, combine the imaginary numbers, and there's your answer.
So, what about division? This one's a little different. It's less of a straight-up calculation and more like solving a puzzle. See, we can't really divide by an imaginary number directly, so we need a clever little tool to change the problem into something we can solve.
So here's the problem. We have an I in the denominator, the bottom of the fraction, and our final answer has to be in that clean a plus bi format. To get there, the bottom of the fraction has to be a plain old real number. So the big question is, how in the world do we get rid of that I? Well, the special tool for this job is called the complex conjugate, and it sounds fancy, but it is so simple. To get the conjugate of a number, you just flip the sign of the imaginary part. That's it. So the conjugate of a plus bi is a minus bi.
And why is this thing so useful? Because of this one magical property. Whenever you multiply any complex number by its own conjugate, the imaginary parts completely cancel each other out. You're always left with just a single, positive, real number. And that is exactly what we need to fix our denominator.
Okay, let's watch it in action. Our problem is that -1 plus I on the bottom. So we find its conjugate, which is -1 minus I. Then we multiply both the top and the bottom of the fraction by that conjugate. On the bottom, poof, the i's vanish, leaving us with a simple 2. On the top, we just FOIL and simplify, which gives us -2 minus 6i. Now we can finally divide, and we get our clean answer, -1 minus 3i. Puzzle solved.
So we've got the rules down. Addition, subtraction, multiplication, division. But what does any of this actually mean? This is where it gets really beautiful. All of these abstract rules, They have a secret life. They describe a physical action.
To see this, we need to picture something called the complex plane. Imagine a normal graph, but instead of an x and a y-axis, the horizontal axis is for real numbers and the vertical axis for imaginary numbers. All of a sudden, a number like 3 plus 4i isn't just a formula, it's a location, a specific point in space.
So let's try a little experiment. Here's our point, 3 plus 4i, just sitting there on the plane. Now, based on the rules we just learned, what do you think would happen to this point if we multiply the whole thing by I?
Well, the algebra gives us a new number, -4 plus 3i. Okay, but now look at where it is on the plane. The point has jumped from the upper right quadrant all the way to the upper left. It's been rotated exactly 90 degrees counterclockwise around the center. And that was no accident. If we multiply by I again, it rotates another 90 degrees, and again another 90. And one last time. It rotates right back to where we started, a full 360 degrees circle. This is the big secret. Multiplying by I is rotation.
And this idea holds true for all complex multiplication. Anytime you multiply two complex numbers, what you're really doing is multiplying their distances from the center and adding their angles of rotation. The algebra, it's not just a bunch of symbols. It's a physical transformation. It's a stretching and a turning in space.
This quote just nails it perfectly. The geometric interpretation of multiplication is stretching and rotation. Every time you do the math, you're performing those physical actions. And this is exactly why complex numbers are so critical in physics, engineering, and signal processing, any field that has to deal with waves or vibrations or rotations. So we started with a little paradox that seemed to break all the rules of math, and we ended up with this elegant, predictable geometry. These weird rules for so-called imaginary numbers actually describe beautiful real-world rotations. It kind of makes you wonder, doesn't it? What other amazing secrets are hiding in plain sight inside the math we think we already know?